Welcome back to G Fun Facts Online. Today, we are not just talking about a faster computer. We are talking about the end of a specific history of computing and the beginning of something entirely new. For decades, the story of computers was linear. It went from vacuum tubes to transistors, from the Intel 4004 to warehouse-sized supercomputers like Frontier. The metric was always the same: add more transistors, get higher clock speeds, and simulate more data. But in late 2019, and definitively in December 2024, with the unveiling of the Willow processor, that linear narrative shattered. We have entered the era of quantum supremacy. This isn't just about speed. It is about a fundamental divergence in how we process information. While classical supercomputers are hitting the physical walls of Moore's law, we now have machines powered by superconducting loops of niobium and aluminum, cooled to temperatures colder than deep space, solving problems that would take the best classical supercomputers trillions of years. In this episode, we are going to tear apart the physics of the transmon qubit, look at the engineering inside dilution refrigerators, and break down the fierce race between Google, IBM, and China's USTC. To understand why a quantum processor like Google's Willow or China's Zuchongzhi is a big deal, we have to start with the physics of the impossible. Quantum mechanics usually deals with the very small atoms and photons. In that world, things can exist in multiple states at once, known as superposition, and influence each other instantly, which is entanglement. Building a computer out of these states is incredibly difficult because they are fragile. It is like trying to balance a pyramid of playing cards in the middle of a hurricane. The leading approach to taming this chaos is the superconducting qubit. Unlike other methods that use trapped ions or lasers, superconducting computing uses macroscopic circuits that act like artificial atoms. The workhorse of this field is the transmon qubit. At the core of a transmon is the phenomenon of superconductivity. When you cool materials like aluminum or niobium down to nearly absolute zero, they lose all electrical resistance. The electrons, which usually repel each other, pair up into what are called Cooper pairs. These pairs move through the metal without scattering, meaning there is zero friction and zero heat loss. But a simple loop of superconducting wire isn't enough. A simple loop acts like a harmonic oscillator, where the energy levels are equally spaced, like the rungs of a ladder. This is useless for computing, because if you try to push the system from a 0 state to a 1 state, you might accidentally push it to a 2 or a 3. You can't isolate the logic bits. This is where the magic component comes in, the Josephson junction. This is a tiny sandwich of two superconducting layers, separated by an ultra-thin insulating barrier. Cooper pairs can tunnel through this barrier. This junction acts as a nonlinear inductor. It changes the energy ladder. It makes the gap between state 0 and state 1 different from the gap between state 1 and state 2. This property, called anharmonicity, allows engineers to hit the qubit with a specific microwave pulse to flip it from 0 to 1 without triggering the higher states. The Josephson junction effectively turns a circuit board into a controllable, artificial atom. These chips are incredibly sensitive. A stray photon or a vibration can cause decoherence, collapsing the quantum state. That is why chips like Sycamore and Willow live inside dilution refrigerators. These look like gold-plated chandeliers. They circulate a mix of helium-3 and helium-4 isotopes to cool the processor down to 10 or 20 millikelvin. That is a fraction of a degree above absolute zero and significantly colder than the empty vacuum of outer space. In this frozen silence, the thermal noise is muted, allowing the control electronics to speak to the qubits. Now, let's talk about the controversial term, quantum supremacy. This term was coined in 2012 by John Preskill. It does not mean quantum computers are better at everything. It marks a specific milestone. The moment a programmable quantum device performs a task that no classical computer can perform in a feasible amount of time. To prove this, researchers use a stress test called random circuit sampling. Imagine a grid of qubits. You apply random operations to them, entangling them and rotating them. As the circuit gets deeper, the quantum state becomes a complex superposition of all possible outcomes. If you have 50 qubits, you are dealing with about 1 quadrillion states. If you have 105 qubits, the number of states exceeds the number of atoms in the visible universe. A classical supercomputer has to track the probability of every single one of those states. It simply runs out of RAM. The race to prove this has been intense. It started with a Sputnik moment in 2019. Google's Sycamore processor, with 53 qubits, performed a random sampling task in 200 seconds. Google claimed the world's fastest supercomputer at the time, IBM Summit, would take 10,000 years to do the same. IBM disputed this, saying they could optimize it down to 2.5 days, but the gap was already opening. Then, researchers at the University of Science and Technology of China, or USTC, struck back. Between 2021 and 2025, they released the Zuchongzhi processors. Zuchongzhi 3.0, released in March 2025, is a monster 105-qubit processor. The team claimed it was 1 quadrillion times faster than supercomputers for specific sampling tasks, utilizing a flip-chip architecture to improve connectivity. However, The debate effectively ended in December 2024 with Google's Willow chip. Willow also features 105 qubits, but with advanced tunable couplers to turn off interactions between qubits when they aren't needed, reducing noise. Willow executed a benchmark in 5 minutes that Google projected would take a classical supercomputer 10 septillion years. That is a 1 followed by 25 zeros. That is longer than the age of the universe. At that scale, no amount of RAM expansion or GPU clustering can bridge the gap. For that specific problem, the race is over. But speed isn't the only goal. The holy grail is reliability. Qubits are noisy. In classical computing, if you want to store a bit safely, you just copy it. In quantum mechanics, the no-cloning theorem says you cannot copy unknown quantum states. So we have to use quantum error correction, specifically something called the surface code. This involves building a logical qubit out of many physical qubits. Some qubits hold data, while their neighbors constantly measure them to check for errors. For years, there was a paradox. Adding more physical qubits introduced more noise than it fixed, but the Willow chip achieved a historic breakthrough: exponential error suppression. Google demonstrated that as they increased the size of the logical qubit, the error rate actually went down. This proves that we have crossed the threshold where error correction works. It is the green light for building million-qubit systems. Let's look at the different philosophies driving this industry. You have Google Quantum AI, the supremacy camp. They focus on proving the math first, with abstract benchmarks to force hardware improvements. Their secret weapon is the tunable coupler, which drastically reduces crosstalk between qubits. Then you have IBM, the utility camp. IBM focuses on transparency and putting chips on the cloud. They have scaled rapidly from the Eagle to the Osprey to the Condor processors. Recently, with their Heron chip, they pivoted back to quality over quantity, aiming for full fault tolerance by 2029 with their Blue Jay and Starling systems. IBM champions quantum-centric supercomputing, where quantum chips work alongside classical CPUs to handle the heavy lifting. Finally, there is the high-dimensional camp led by China's USTC. Their Zuchongzhi series and the photonic Zuchongzhi system are focused on national strategic dominance, achieving benchmarks that are undeniably beyond classical reach using high-density interconnects. There is one massive factor that often gets overlooked: sustainability. To simulate the random circuit sampling task from 2019, a supercomputer like IBM Summit consumes about 14 megawatts of power. That is enough to power a small city. Google Sycamore, doing the same work, consumed about 26 kilowatts. And most of that power wasn't even for the chip, it was for the pumps in the refrigerator. The chip itself runs on milliwatts because superconductors have zero resistance. As we move into an AI era where model training consumes gigawatts, quantum computing offers a path to green high-performance computing. For optimization problems, like protein folding or energy grid distribution, a quantum computer could arrive at a solution using a tiny fraction of the energy required by a massive GPU cluster. So what does the road ahead look like? We are currently transitioning from the noisy intermediate-scale quantum era to the fault-tolerant era. From 2026 to 2028, the goal is not just more qubits, but better logical qubits. The aim is a forever qubit that lasts indefinitely, because error correction is faster than error generation. By 2029 and 2030, we expect to see the first commercial utility. This means solving problems that justify the cost. A prime target is nitrogen fixation. We currently use the Haber-Bosch process to make fertilizer, which consumes about 2% of the world's natural gas. Quantum computers could simulate the FeMoco enzyme to learn how to do this efficiently, potentially revolutionizing agriculture. Another target is battery chemistry, modeling lithium interactions at the atomic level to double electric vehicle range. Of course, there is the threat known as Q-Day. There is a fear that a large enough quantum computer running Shor's algorithm could crack RSA encryption, which protects the internet. Estimates suggest we need about 20 million physical qubits to break 2048-bit RSA. With Willow at 105 qubits, we are far away from that. However, the threat of store now, decrypt later is real, which is why agencies are already standardizing post-quantum cryptography. To wrap this up, quantum supremacy is no longer a theory, it is an experimental reality. The Google Willow chip and China's Zuchongzhi 3.0 have proven that we can engineer systems that manipulate information in a mathematical space so vast that classical physics cannot contain it. We have moved from the vacuum tube era of quantum computing into the transistor era. The engineering challenges of scaling cabling and control systems are immense, but the physics works. The gate has been opened. We are no longer just computing. We are choreographing the fundamental fabric of the universe to do our math for us. Thanks for listening to G Fun Facts Online. We will see you in the next deep dive.